splits into 2 ions of batteries. Batteries. Okay, so we'd have to take the square root of 8.8 times 10 to the minus 11. Okay, so this is for manganese carbonate. This is about 9.4 times 10 to the minus 6. And then the silver phosphate. Of course, it splits up into 4 ions. So now let's see. KSP is equal to, with 4 ions.
27 x 2.
Is that right? Did you remember correctly? It's
Yeah,
27x to
27x
the 4th, right?
Yes.
So that means, let's see, that means x is equal to the KSP value divided by 27. Then we'll have to take the 4th root of that, right?
It's pretty simple.
Okay, so let's see what that gives us. So let's see.
We don't need it.
You already got it? What is it?
We only get the polygons on the end.
Couldn't quite hear the exponent. So, which salt has the greater solubility?
83 pure.
It is the silver phosphate. Even though it's got a smaller KSP, you notice that splitting into more ions helps the solubility, right? Makes X bigger. What do you think of that? Too good? This is like KSP 101, right? The basic stuff with KSP. Can I flip slides?
You're gonna hold this for a bit. You're gonna hold this for a bit.
I'm sorry, I can't.
We're going to save that.
Because I have some disease on my head.
Let's save that for a moment.
When he gets nervous, he gets to stop the other people. I'm not even kidding.
Come on, Isaac.
Now let's look at the bottom of this slide. I'm starting here. Some salts have a pH component to their solubility. How many people love the Chatelier's principle? Only 2. All the Chatelier lovers left the room, I guess. Thank you for those of you who stayed. This is a great example of the Chatelier's principle. I don't know why you guys don't like Le Chatelier. It's easy. I mean, maybe it's the name.
But it's also like the Drew. They call it the Drew.
Mr. Hamilton family. The question was that no one was raising their hands, and then when you asked the question, some of us raised their hands, and that made us, the rest of us not want to.
Performative.
I missed the first part.
If
of
we
it. I'm
if we
sorry.
renamed it like Drew, it'd be better.
Rename it. I missed Nick's point too.
We were too lazy to raise our hands.
Too lazy. It's just pure laziness.
Yeah.
All right. We're looking at the bottom of this slide here. All right, so here's the point with some of these salts. Like my first example there is silver chloride. You may remember from way back when, most chlorides are soluble, except silver chloride,
Lead.
lead 2 chloride,
And some other.
mercury 1 chloride. Yep. So, you've got this, let's say silver chloride precipitate. You'd like to dissolve it. So you're thinking, I'll bet you if I add some acid that'll help. Okay, so you come along and you start adding some hydrogen ions, right?
So those are the really small.
Okay, so now the thought is that, is there any tendency for chloride ions to stick to hydrogen ions? And the answer is no, because that would be HCl, that's a strong acid, 100% ionization. So because these two are never going to stick together, there's no effect. There's no effect. But if we made a little bit of a change here, instead of silver chloride, what if it was silver fluoride as a precipitate? Okay, because now when you start to add the acid, of course, HF is a weak acid, which means the hydrogen and fluoride ions are going to start sticking to each other. Here's the Le Chatelier's principle. If the fluoride concentration starts to drop, right, because we're taking fluoride out, then which way does equilibrium shift? Goes to the right, right? You start to ionize to replace the fluoride ions, which means the solubility of AgF goes up. Right, so if you had a silver fluoride precipitate, you could start to drop some acid in with it, and you would start to make it dissolve. Essentially what you have to look out for are salts that have an anion that's part of a weak acid, right? Watch out for a weak ion or conjugate bases of weak acids.
So you could technically, if you added make it more basic, you could do the same thing. Like,
Okay, so you're talking about this example, are you?
if you add base, then
Well, let's see, if you start dumping it, it may be a little different effect though. I don't think these two are not going to really interact, right? But silver hydroxide is not very soluble. And so what would happen is some of these silver ions would probably start sticking to hydroxides. Now you'd have battling KSP values, right? Because you'd have a KSP for silver hydroxide. You have a KSP for this guy. And so whoever's the least soluble, right, smaller KSP, that's what's going to precipitate out because it doesn't, it's the least soluble.
it'll increase the solubility for the other one.
Yes. That'd be an interesting thing. So you'd be trading one precipitate for the other. You're like a precipitate swap. So what do you think? If you were looking at a list of salts, could you pick out the ones that are pH sensitive this way, ones that if you were to add some acid lower the pH, they'd start to dissolve? Do you remember who your strong acids are? It's actually a shorter list. You see who's not going to be affected by the addition of acid. Who will not be? Any ideas who's not affected by adding an acid?
D.
Okay, so D, I thought I heard a D out there, right? I'm thinking, well, sulfuric acid, H2SO4, that's a strong acid, so adding acid probably isn't going to affect this. Or, I think F, right? Because HBr, that's a strong acid, so adding acid wouldn't affect. But the others should be affected. Right? Like the chromium hydroxide, that's a little bit different reaction, but it's the same idea. Right, if you start dropping in some acid all of a sudden, do you see what reaction will start to take place?
1 times 2
Now, are you seeing those two neutralizing each other? Right, you start to make some water, and this will start to ionize more. What do you think? There's another sort of basic piece of KSP knowledge.
We normally the 1 times 4 times 10 negative 7.
And what about it?
Because I saw it from the test where it says when there is a OH or H in the.
That's something different. We're not crunching numbers with this yet. You're ahead of us.
Because I saw it from the test.
Yeah. I know what you're talking about. We just haven't gotten it yet. All right. Let's see, where are we going next? Not there. Here. Okay, I would say the next thing maybe to mention today is the common ion effect. We actually saw this in chapter 15. It is what started our buffer discussion. The common ion effect. Zakir, is this turning out at all, do you think?
Yeah.
Is it? Thank you for doing
No problem.
If I was you, I would, get some copyright going on this so they'd have to buy it. Maybe we can rig something up that'll like charge them automatically and they'll try to download this. You can just take money right out of their bank account and download it.
Make me do a survey. Every time you download, make me do a survey.
What's that? That's right.
Put this on I can get to buy this podcast.
Okay. So the common ion effect is when you're trying to dissolve a salt into some water that already has one of the ions in it. Okay, so let me do it in English they would call compare and contrast. Do they still make you guys do that stuff? Compare and contrast papers? I remember doing those many moons ago. When I decided, I'm not going to do this. Not going to happen. Okay, so my example was with lead 2 sulfate. Is this purple fading out?
A little bit.
Can you still see it? Let me know if you can't see it, because it's starting to go. I should try this. I think somebody told me if you put a little bit of acetone in here, you can get more of the ink to dissolve.
Acid?
I gotta try that. Anyways, if you're gonna do this in pure water, if you said, hey, what's the solubility of lead 2 sulfate in pure water? Are you thinking you could do this quick and easy?
Yes.
You would just do what? Be specific. What formula are you going to do?
X squared.
Are you thinking, hey, yeah, this is a 2-ion salt, X equals the square root of KSP, right? Piece of cake. If my memory wasn't going, I could remember that number from last hour, but I don't. Okay, so we need the square root of 3 minus 8. It's about 1.1 times 10 to the minus 4. Pure water. Okay, now my example here is, what if you're trying to dissolve that same lead sulfate into a solution that's 0.2 molarity for the sulfate ion? Well, okay, but we're going to have to think about the ice table now. Okay, here's the difference. In pure water, when we were doing our shortcut to the ice table, both ions initially were 0.